To find the EMF, first we have to find the magnetic flux in the square loop of wire, and flux will change depending on magnetic field and area. In this one, the magnetic field is staying the same, but it depends on where we're taking the small section of the derivative for, because the further away from the wire you get, the area changes. So you can take an arbitrary slice, which I call R, and so the area is going to be length times dr, which is going to give you dA. So the magnetic flux is going to be equal to B dA. And we can ignore cosine theta because it's the loop and the wire are both on the same plane and they're parallel to one another. So cosine of theta is just going to be 1, so we can ignore that. To solve, you have to take the integral with respect to r from d to d plus t, and the distance, which is just the distance from the wire, so d and l. Everything can be taken out of the integral except for 1 over r. So you get this equation here. So to find EMF, you have to take the derivative with respect to time. And so everything can be taken out of the derivative except for e to the negative t over rc. And using the chain rule, the derivative becomes negative 1 over rc times the original, which is simplified to this equation here. So for part 2, if we assume that the current is going in this direction up, we know that the magnetic field is going to be turning around the loop this way because of the first right-hand rule, which means the field through the loop is going into the page and decreasing. So an induced EMF will be created that's going in the same direction into the page, and the induced field creates a current that goes around the loop clockwise. So the field in the loop creates a current in the wire because the wire is going to have a current created from outside sources. It can't create one from its own field. So the current in the wire is going to be acting in the same direction as that of the loop. And because currents are going in the same direction, that means that the loop is going to be pulled towards the wire because they're attracted to each other.